Okay. All right, so we're almost done with our discussion on momentum, impulse, and Newton's second law. I believe it's time, right? Yeah, it's right at 11. So let's go ahead and get started. Perfectly inelastic collision. So we already looked at, what did we look at? Drawing a blank. We saw conservation of linear impulse and momentum. And we kind of talked about the difference between elastic and inelastic collisions. I did get a couple of questions, which I'm always happy to get questions, guys. You don't understand. If your opinion is that you think that you're bothering me, at least in my case, if you think you're bothering me by sending me emails and asking me questions, you're not at all. It actually makes me very happy that people are concerned about learning the material. So do not apologize for asking or sending me emails, asking questions. I appreciate it. I actually appreciate it, and it makes me all warm and fuzzy inside. But I want to hear your questions. Okay, so if you end up with a question while you're doing the homework, do not hesitate to write to me, because I actually do appreciate it. I want to hear your questions. All right, so that being said, so let's talk about what perfectly inelastic collisions are. And that it's just the definition. We'd say perfectly, but inelastic is inelastic. And again, perfectly inelastic collisions, actually it's the other way around. Elastic is elastic. By perfectly inelastic, we mean that the objects collide and they stick together. So all the, like in the mud, whenever I gave you the example of the mud falling into the, still have somebody in the waiting room. Give me a second. This thing's, there we go. That'll work better. Like in the mud, it completely sticks in. That's perfectly inelastic. All right. So perfectly inelastic collisions do not conserve energy. And as I just explained, objects begin as, it's one of two things. Either objects begin, I don't like the way that I worded it in my notes, so I'm trying to, objects begin as two separate bodies. They collide and then stick together. The way in my notes makes it a little bit confusing. So, all right, so we've got two separate bodies. So this is very common in car wrecks. Well, you'll have two cars, they might hit and they connect and they spin off together and they intertwine. That would be a perfectly inelastic collision. They collide and they stick together. They become kind of like one big mass and they go off, right? So you got the mass of this car and the mass of this car, and they hit each other. They collide, they stick together, and they go off and become one big mass. That's a perfectly inelastic collision. Another example might be this one. Let's say we've got anybody who's watched Mythbusters. I know it's kind of an older show now, but anybody who's watched Mythbusters know that they do this, the bullet gel thing, and they'll shoot something into the bullet gel. And so you have a bullet over here, and we can call that M1. And then we have the gel. I don't know what the technical term for that stuff is, because I'm not much into stuff like that. I'd like to learn how to shoot and stuff, but go hunting. That's not something I grew up with anyway. You shoot into the gel, And then after it gets, okay, it goes into the gel, and these things become one big mass. We're going to ignore the fact that some of that gel might get spit out of the back end whenever the, as it's displaced. But this becomes one big mass, M1 plus M2. All right. And so you have an initial velocity for V1 here going off in this direction. The initial mass for V2 would be 0. Okay, and then over here we have one combined velocity, V final. And so up here, this would be the left-hand side of our equation, right? We would have an M1, how do I put this? Let me do this properly. So we would have a V1I times M1 plus a V2I times M2, right? And then down here we would have M1 plus M2 times V final. And so our equation down here would look like, make sure I keep this in order. V1I times M1 plus V2I times M2 equal to M1 plus M2 VF. So basically it's just the momentum of the bullet, right? This would be the momentum of the bullet. This would be the momentum of the gel. And this would be the momentum of the combined bullet and gel. Okay, so that's one situation. Another situation would be like if something has a mass and velocity, and then something happens where they break apart, like maybe like keep going with all of these violent things, like a grenade. A grenade would do that. Maybe like if you were to throw Jello, maybe if you threw it hard enough, you'd start, and then the velocity. Ooh, okay, I can do that later. And then it breaks apart. Okay, that would be an example. But so if we were to draw it out, then we would have, let's say, a ball or something, and it's got a mass, a total mass here, and it's got an initial velocity VI going that way. And then sometime later it breaks apart. So we'll have like part of the ball going off in this direction. Let's keep it linear. Let's keep it all along the X line. So it goes that way, and then that part goes off that way. So we'd have an M1 plus an M2 because it splits into two parts. So the mass is going to split into two parts. And each mass is going to have a different velocity. Right. And so our equation here would look like the total mass M times VI equals to M1 V1F plus M2 V2F. Okay. So looking at an example. We have our bullets. It's just that we use a lot of bullets and stuff in these because they're the most common and most obvious examples for this stuff. So hopefully nobody's getting upset about that. I know some people might get upset about that. We got a 10-gram bullet moving at 343 meters per second. and it collides and sticks in 114 kilogram wooden block at rest. After the collision, what is the speed of the bullet and the block, right? So we've got the beginning situation, the beginning state, and then all the ending stuff. All right, so at the beginning, we have a bullet and we have a block, right? The block is at rest. So V for the block, we'll call that block A. The initial speed of the block is 0. The mass of A is 14 kilograms. I didn't like my bullet. Okay, plus. And the bullet has a mass, so I'm going to call that M little b. Has a mass of 10 grams, so that's going to be 0.01 kilograms. And it's going at a velocity, initial velocity of 343 meters per second. So no conversions there. And then at the end, it says that after the collision, the speed of, what is the speed of the bullet and block? So they put it, it's in with hyphens, or yeah, there to say that they're connected now. So the bullet's embedded inside of the block now. Okay, so we have the masses added together, MB plus MA, and it's asking what's the final velocity. And we just multiply those things together. We just get the momentums of each one of these separate. So this is going to be a 0.01 times a 343. It is going positive, so we are assuming that it's going that way. Plus, this one is going to be a 14.0 times 0 equal to MB was 0.01. Oops, plus 14.0 times VF, right? And then we just solve that for VF. So that would be 0.245 meters per second. I'm not going to go through all the algebra, but that's what we would end up with. Right. So let's do a variation. Even though it's not this is not, wouldn't be in the inelastic example, but let's just do a kind of a variation, or perfectly inelastic, I should say. The variation here is that a bullet, let's say the bullet passes through the block and ends with a final velocity of 100 meters per second. Okay, in that case, the beginning would be set up the same. Right, we'll call that A, and B is still 0.01 kilograms, and it still starts with a 343? I can't read my handwriting. 343. Same here, the block still has 14 kilogram mass, and the initial velocity I is 0 meters per second. And this is going to be equal to, right? So this, after it's passing through the block is still going to gain some velocity as the bullet passes through. The mass doesn't change, it's still 14.0. Well, it'll change a little bit, but we're going to ignore that. And it's going to end with some final velocity plus, and the bullet slowed down because some of that energy went into the block. So now the bullet slowed down. It's still going this way because it passes through, so it's still going in the same direction. It's still 0.01 kilograms, but our final velocity for the bullet is going to be 100 meters per second. Right. So in this case, we would still be the same idea. It's mass times velocity. So we have a 0.01 times 343 plus 14.0 times 0. And that's going to equal to a 14.0 times VAF plus 0.01 times 100. And again, I'm not going to go through all the algebra of that. Just kind of we have to end a little bit early today, but thankfully this is really short to explain. These concepts are pretty easy. I hope they're pretty easy for you guys anyway. So anyway, after you do the algebra, you should end up with a 0.174 meters per second. Any questions? Cool. All right. So that was inelastic. Let's look at elastic collisions. As I stated on Wednesday, excuse me, sorry. Elastic collisions conserve energy. Right, so the change in E is equal to 0. And most of the time that means that the initial and final kinetic energies are going to be equal. Right, and by I mean most of the time, because most of the time whenever we're dealing with collisions like that, we're just looking in the x directions, but collisions could happen in the y direction as well. So maybe I'm throwing a ball up and there's another ball coming down and they collide in the air. That's just that's not something we see very often, so we don't really consider it too much. Yeah, so it conserves energy if, and I explained that part here, if collisions occur in a plane then it's just what I wrote up there, Ki equals to Kf. So maybe I should just leave that off here and just put it down there. Okay, so that statement is true. And then we have that P is equal to M times V. Solving that for V, we have that V is equal to P over M. And then I can replace that here. So I'm going to end up with K equal to 1/2 M P over M squared. So my kinetic energy is going to be equal to 1/2 times P squared over M. Okay, so either one of these equations will work with these collisions, right? If I can find the momentum and square that, then I have the kinetic energy. Because elastic collisions conserve energy, we will usually need two equations to solve for two unknowns. Okay. So most elastic collisions most elastic collision problems will require two equations to solve for two unknowns. All right. And so we would need the two equations we would need was the first one would be conservation of momentum. So the sum of all of the masses times the velocity, initial velocities, is going to equal to the sum of all the masses times the final velocity. So the sum of all the initial momentums is going to be equal to all the sum of all the final momentums. All right, so that equation. And then we would need the conservation of energy equation, which I've already written several times now, that Ki is equal to Kf. I've already written that a couple times. Okay. What's the problem on that? So I'll give you guys a second. This one takes a little bit longer to write down, so I'll let you guys write this one down. We have some time, so we have a lot of time. Okay, hopefully you guys got that down. Here we have a example 5. A professional baseball pitcher throws a 225-gram baseball with a speed of 42 meters per second at a wall. All right, so the ball bounces back with a little loss of kinetic energy, very little. All right, so it says very little, or it says a little bit of loss because so that we can assume an elastic collision. All right, what is the recoil speed of Earth? If the mass of the Earth is 5.98 times 10 to the 24th kilograms. All right, so this is the type of thing we're looking for again to find out if it's an elastic collision. An elastic collision, again, I said this on Wednesday, but I'm going to repeat it here. An elastic collision will either say it's elastic, or the problem will say energy is conserved. or no energy loss or something like that. Or an example like this, where we've got this small little ball and this huge other thing, and it says something like this, a little loss of kinetic energy, we can assume elastic collision. Okay. So those are the three ways we know it's an elastic collision. If it doesn't say anything like this in the problem, then it's going to be an inelastic collision, right? It has to say something like it is elastic collision, or it has to say something like energy is conserved, or there's no loss of energy, or it has to say something like this problem, there's a little bit of loss of energy. And then we can assume elastic collision, all right? For this problem, let's draw it. We've got our baseball. We're given the mass of that baseball equal to 225 grams, so that's 0.225 kilograms. And we're given an initial velocity for the ball of 42 meters per second. And here's the Earth. And we're going to assume that the wall is a part of the Earth. So I'm going to kind of exaggerate. I'm exaggerating the drawing here. So this is the Earth. This is the wall. Right? And the ball is going to hit that wall, right? So the velocity of the wall, we're going to assume that at that moment it's zero. We're going to assume zero relative to the Earth. And we were given the mass of Earth as because the wall is going to be, it's connected to the Earth, so it's going to be part of the mass of the Earth, right? So it's going to be 5.98 times 10 to the 24th kilograms. Afterwards, the ball rebounds. So its velocity goes the other direction with little loss of kinetic energy. So that means the final velocity is going to be about the same as the initial velocity. So this is going to be VB final is going to be, it's just going in the opposite direction. So negative 42.0 meters per second. Okay, this is getting in the way. Let me grab all this and move it real quick. Plus the wall's now moved a little bit. We're going to assume it's moved. I'm going to exaggerate that movement because obviously it's not going to be a whole lot, but right. So it ends with some velocity final equal to, we don't know. And the mass of the Earth is still the same. So mass is still 5.98. Times 10 to the 24th. And the mass over here of the ball is still 0.225 kilograms. And that's the setup, right? Kind of a silly little problem, but it's somewhat realistic. Okay, so 0.225 times that speed of 42.0 kilograms plus, this is going to be zero, so I'm just going to write zero, is equal to 0.225 times the negative, don't forget, it's going to the left, so it is a negative 42.0 kilograms plus the 5.98 times 10 to the 24th times V of the wall final. Yeah. Right, so I'll go ahead and do, we got a lot of time, so I'm going to go ahead and do, this is going to be, I think I already have it. This is going to be 18.9 on the left-hand side. This is going to be 5.98 times 10 to the 24th V wall final. And then dividing both sides, we're going to end up with a V wall, the final velocity for the wall equal to 3.16, and get this one, times 10 to the negative 24 meters per second. All right, so I believe I have this written out with all the zeros somewhere. Let me see what it is. It's probably here. I just like to show off all the zeros, just a lot of zeros. So it's 3.16, and we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Running out of space. 23, 24 meters per second. Let me make sure that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24. Yeah. So that's how fast that wall is traveling after the baseball hits the wall. Okay, so very, 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 very slow. So slow that we wouldn't even notice it. And we don't, right? Whenever I throw a baseball at a wall, I don't notice the whole earth moving at all. Why? Because it's practically zero. So just a funny little problem there that we can kind of estimate what goes on a global scale whenever something happens like this. And that is momentum, impulse, and Newton's second law. That's the end of that. On Monday, I believe we get into vectors. I will spend the rest of the week on the vectors. And then we will have spring break, and then we'll come back and we'll deal with 2D motion, and then we'll have exam 2. We're done for the day. Are there any questions over any of the material from this section of notes, the momentum, impulse, and Newton's second law?
For now, I just wanted to ask if do you know when this recording will get posted?
Yeah, I haven't done the one for Wednesday yet, but I try to always post them. I think it's the only one I haven't posted this week, and I'll post both of them today at some point. Yeah, I try to get those as soon as I can, but sometimes I'm not always able to do it immediately. Yeah, I got part 1 up, so I just need to get part 2 and 3 up. I apologize for that. I used to edit these things. I used to take time to edit these things, and it was like, it's too much. I'm not editing anymore, and I just put it up as it is. Unless I think there's something that maybe might be a little bit too private on y'all's end. Like maybe you guys were asking something and I didn't want it to be out on YouTube. I'll edit that out, but otherwise I just post them. All right, guys. Go ahead.
Oh, nothing. I just said that was
okay. All right. I'll see y'all on Monday. Have a great weekend. And of course, if you have any questions on the homework, send them to me. Email me.
Thank you, sir.
Thank you, sir.
Right. Bye, guys.
Bye, sir.
Bye.
Bye, sir.
Bye, everybody.